Okay, today we will continue our discussion in overview of OS principles. Okay. Last time we said discussion about dynamic loading for shared library. Okay, we mentioned that a routine can be loaded into memory when it is needed. Okay, because a lot of time, most of the time, the error handling routines, they are not used during the wrong time. Okay, so a good programming or process management mechanism is that you try to you will not load all these error handling routine into memory until they are referenced. Okay, so this kind of mechanism or technique or concept can be used for memory management also. Okay, because when we execute a process, as long as the instruction and related memory location are in memory, then this particular instruction can be executed. If we try to execute an instruction and some related or referenced memory location is not in memory yet, then operating system can take it, can be triggered to take over and load those referenced memory into the uh, into the physical memory, then restart the instruction. Okay, so this kind of mechanism we give a general term called virtual memory management. Okay, the basic idea is that we separate the user logical address space from the physical memories. Okay, when execute a program on those logical address space, they are currently needed put in or loaded into memory. Those part of the program image, they are not currently needed, will be in backing store until they are referenced. Okay, so in a sense that because whenever we try to execute a program, the currently the memory location they are currently needed usually is far less than the physical memory. Uh, okay, so it's possible you can create a very large virtual memory space for a program or process and run this process in a much smaller physical memory environment. Okay, so that's the reason that a logical address space now can be much larger than physical address space. Okay, because we only load those parts they are currently needed into the physical memory. Okay, those part of program or processor memory image they are not currently used, then you put it in the backing store. Okay, so then the physical memory can be shared by as many as process as possible. Okay, because every process only load a small portion of the process in the memory, only those portion of the address space they are currently needed. Okay, so the memory overall memory utilization can be much efficient than. Okay, so an extreme situation is that whenever we create a new process, we allow allocate zero physical memory to the process, and this kind of mechanism we call demand paging. Okay, so it means when a page is needed, then we load it into memory. So initially, if a process first created, we maybe assign only one page into the memory or 0 page in the memory. So the first instruction we try to run the process will cause the operating system be triggered to take over. And though the page that the first instruction is registered, okay, into the physical memory. Okay, so that's sometimes we call this kind of mechanism pure demand paging. Okay, demand paging means we load a page into the physical memory when it is needed. Pure demand paging means a process created without any physical memory allocation. Okay. Okay. So the concept is that the virtual memory or the logical address space, okay, can be much larger than the physical memory. Okay, therefore a process, for example, in this case, the total image is from 0 to maximum, and we divide them into page 0 to page V. Okay, and V, and the physical memory only is a smaller number of physical frames. Okay, and this virtual memory, we have a memory mapper or page table. We keep track which logical page is allocated into which physical memory. And if a logical page is not allocated into the physical memory yet, then in the memory mapper we just store or reflect this situation. Okay, and usually a flag can be used to indicate either this logical page is in memory or not. Okay, so demand page formally we can define that it's the system bring the page into memory only when it is needed. And we use a flag bit, we call it in a page table entry, called valid bit. Valid means the page is in memory. Okay, it's a valid mapping. Invalid, or sometimes it's invalid reference or page is not in memory. Okay, so invalid may means two things. One is invalid reference. The second one is the page is not in memory yet. Okay, so when we try to reference a page which is invalid, the valid bit is invalid, then a trap trigger to operation, and this kind of trap we call it page fault exception. Okay, the operation will check process control block to find out, okay, where this page is located in the physical in the backing store, and then bring in those particular page into the main memory. Okay, if the page, the embedded reference, okay, the embedded bit is caused by embedded reference, then that means it's out of memory, out of bound exception. And the process refer to a page which is not in the logical space. Okay, not in memory will cause a swapping, the swap in the missing pages. Okay, or the demanded pages. Okay, and sometimes we use a swapper. It called lazy swapper. That means it never swap in a page until it is needed. Okay, a swapper which used with paging system, sometimes we call this kind of swapper pager. Okay, okay. But swapping is a technique which bring the process into memory, physical memory, or bring a process out of physical memory. Okay, and if the swapper, the unit of swap in and swap out is the page, then this kind of swapper sometimes we call it pager. Okay, so embedded in the page table entry means two things. One is the reference is out of bound, okay, because the logical addressing space is not, okay, it's out of the logical addressing space, okay, and second one is not in memory, okay. Here is an example, okay. If we have a process contain 8 logic pages, okay, so we have logic page 0 to 7. So the corresponding page table will have a entry also, okay. And here, this particular example, only 3 pages are in physical memory. That's page ACF, okay, those pages, and they are stored in physical memory 4, 6, and 9, respectively. So the page table entry, the very embedded bit, okay, only these 3 pages are valid. The other 5 pages, okay, in the page table are all marked as embedded, okay. The page 4, okay, handling, okay, we'll go through something like, okay, we'll try to execute an instruction. For example, we try to load an instruction, which is for example, we try to reference memory location M, okay. And so first thing, the first step, you reference to page table, okay, in this particular page table entry, and find out the very embedded bit is embedded, okay. Then we trap to the operating system, and operating system will validate, okay, if this really an embedded reference, then we abort the process. If the embedded, the reason for embedded is the page is not in memory, it's on backing store. That's the step 4. Then you go to the backing store, bring in its missing pages to the physical memory, okay? And you allocate any free frame to this particular pages, okay? And then configure the corresponding page table entry to change the embedded to be valid, okay? And then return from the operating system to the user process and restart this particular instruction load M, okay? So that's the detail or the conceptual steps required to handle a page 4. Okay, that means a page 4 means that you try to reference a page which is the page table entry has an embedded indication flag. Okay, when this page 4, and the reason for page 4 is that the page is not in the memory, okay? The page is embedded, then the process need to be stopped, okay? Only the page is not in the memory. Then we will try to find a free frame for that particular page and bring in the page into the physical memory. But if there's no free frame when page 4 happen, and a page need to be loaded into the memory, okay, then we need to do some replacement. We need to replace, select a victim from those pages which currently in memory, select one of them as a victim and swap out that particular page, and then bring in the needed pages, okay. So this kind of process we call page replacement, okay. It's a formally defined as the page replacement. It's the process finding a page, okay, and to page out to the disk, create a free frame for the needed page, okay. The objective for page replacement is to minimize, okay, the total number of paging activity. Okay, so a good page replacement policy or upgrade should try to at least try to minimize this paging activity. Okay, because paging is the activity of the paging is an overhead. Okay, because you bring in something into memory, but without doing any actual works for the applications. Okay, so paging, you may need to shuffle the page content between memory and the disk. Okay. To be able to select the right page to page out, in general, we need to we use another flag bit here. We call it modified bit or dirty bit to reduce the overhead of paging. Okay, because if a selected page is modified, that means during its life cycle of residence in memory, the process has modified the content of the particular page. Then, if this kind of page is selected to page out, then we need to write the new content in the physical memory back to the backend store. However, if we select the page which need to be replaced, it's clean. That means no modification for that particular page during its life in memory. Okay, then we don't need to swap it out. Okay, we don't need to write the content back to the backend store because the content is never been changed. Okay, it's the same as the original content in the backend store. Okay, so we only need to bring in the new page. We don't need to store back, modify the page. Okay, so the purpose for using this dirty page or modified bit to recall the situation of each in memory pages is that if a memory page is dirty, then when it is selected to page out, we need to physically move the content back to the restore the content to the backend store. But if the selected page is clean, then we only need to bring in the new page. Okay. So the purpose is that we mark all these in-memory pages, their situation, whether they are modified or not. Okay, only those modified pages, when they are selected as to page out, need to be restored back to the disk. Okay, and unmodified page, you don't need to bring in restore their content because the original content is already in backend store. Okay. Okay, here's it. Let's see this example. Okay, if we have two processes, okay, the first process, both processes has 4 pages, logic pages. Okay, and for the first process, this 4-page table, the memory location M is in logic page 3, but page 3 is invalid. It's not in memory yet. Okay, and for the second process, in the downside, okay, in the bottom half, again we have 3 pages in physical memory, and the page 1 of the second process is invalid also. Okay, so the physical memory has 8 physical frames, but 2 of them are occupied by operating system. Okay, in 0 and 1, and the other 6 frames allocated 3 to first process and 3 to the second process. So currently all the physical frames are occupied. Okay, so when the first process try to issue the instruction load M, and M is logic page 3, then we will see that the logical page 3 will trigger a page 4 because it's not in the memory. Okay, so but a page replacement was needed. Okay, because we try to load process back into M into, and here we select the okay, we need to do the page replacement. Okay, so the replacement is something like here. First, we when we select a friend, for example, here, if the friend F, okay, the page located in friend F is selected as a victim. Okay, so we need to swap out this particular page. Okay, and change its index into embedding. Okay, and then we bring swap in the desired needed page into the friend F. Okay, and we modify the page table entry for corresponding to these new pages, and for the embedded bit marked as a value, and the friend number F will be stored into the friend number fields. Okay, and the original page replaced. The friend number will be marked, become useless because the embedded, the value embedded bit is embedded. Okay. The algorithm used for page replacement, in general, there are 4 typically commonly used. The first one is first in, first out. Okay, all these algorithm, scheduling algorithm or replacement, you can see that time, arriving time. Okay, this kind of algorithm use the arriving time as the determining factor. It's very common. Okay, so we replace the page that in the memory for the longest time. That's the first in, first out. Okay, use the time. Okay, the time bringing the page was bringing to the memory. Okay, to decide which page should be replaced. Okay, the reason behind this is that if a page is in memory for a long time, then probably it's not needed. Okay, so that's the simple argument. Okay, the optimal algorithm, that means we try to replace if we know in advance that this reference, the memory reference in the future. Then we try to always replace the page that will not be used for the longest period of time, starting from now. Okay, from the current time. Okay, so we replace the page which is needed far away from the current time. Okay, in the future. Okay, but in general, it's impossible to know in advance when we need to refer a page. Okay, so it's just an ideal case. It's used as an upper bound. Okay, to compare those different kind of page replacement. Okay, so if we know the reference sequence in advance, then we can use optimal algorithm. Okay. Optimal algorithm will assume we know the future, the reference sequence of the future. Okay, but in no, we only know the reference sequence of the past. Okay, so this recently used algorithm, or sometimes we call it LRU algorithm, is the middle of the optimal. That means because we know the past reference, so we replace page with the first is the time from the last reference. Okay, that means the the last time we reference that page is it's a long time ago. Okay, the last reference to this particular page is long time ago. Okay, then we replace that, because if the page is not used for a very long period of time, then it probably will not be used in the near future. So the philosophy is something like this. Okay, so that's that, and then you can see that it's like a middle of the optimal algorithm. Optimal is try to replace a page which is will not be used in the near future. Okay, the next usage will be far away. Okay, but in here if the previous use of the particular page is far away from now. Okay, it's long time ago. Then we replace that one. That's the RRU. Okay. The last one is we call it clock algorithm, or sometimes we call it second chance algorithm. Okay, that means it's a variation of first in first out. Okay, so it's basically a first in first out, but with a second chance. Okay, that means if a page is referenced during the last page 4, okay, during the period of page 4, the column page 4 and the previous page 4, okay, during this time interval, if a page is modified, is referenced, then we give the page a second chance, something like the basic idea is something. If in the period of page 4s, okay, the column 1 and the previous one, okay, during this time period, a page is not referenced, and it is in those, it is the page which is in memory for a long time and is not referenced during the last page 4 period, then the one will be replaced. Okay, so to recall this information, we can arrange the in-memory pages as a circular list. Okay, on selecting the victim start at its column position and look for a page whose reference bit, okay, are 0. Okay, then if we set the reference bit, if the page with reference bit is 0, the first page, okay, will be selected as a victim. Okay, but if the reference bit is 1, then we set reset the reference bit to 0 and give the page another chance and go to the next position. Okay, so that's sometimes we call it clock. The first in first out algorithm has some special anomaly situation. Okay, because in general, if a process we assign a more physical frame to a particular process, intuitively the number of page 4 in the main paging situation, the number of page 4 occurred should be less than the same process, same reference sequence, okay, with less physical frame numbers. Okay, for example, but however, if the algorithm is first in first out, then sometimes you give more physical frame will generate more page 4. Okay, here is an anomaly example. Okay, assume we have a reference string is something like this. Okay, you refer to page 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. Okay, if you have a 3 frame for this particular process, okay, and it is in the main page, okay, then the first three, 1, 2, 3, they will all generate a page 4 because initially for pure demand page, initially there's no page is in physical memory. Okay, so the page the logical page 1 was reference. Then you need to move in. Okay, in here the red number means page 4 occur. So 1, 2, 3. Okay, and 4 comes in. It will replace the first page, okay, stored in the physical one. And then 1 comes in, replace the second one. And then 2 comes in, replace the third page, okay. And then 5 replace the first page. Okay, at 1 there's no page replacement. Okay, and 2 is no page break. Then 3 comes in, will replace the second page. Okay, 4 comes in, replace the third page. And then 5. So total, we have 9 page 4s. Okay, if we give this same sequence, same process running in the 4 physical frame situation, then we got this 1, 2, 3, 4. They all get page 4, and then 1 will not generate page 4. 2 will not generate page, and then 5 generate page 4. It replaces the first position. Okay, and then 1 replaces the second position, 2 replaces the third position, 3 replaces the fourth position, and then 4 comes in, replaces the first position, and then 5 comes in, replaces the second position. Okay, so overall we generate 10 page 4s. Okay, so it's violated intuition. Okay, so that means more friends may generate more page 4s. You assign more resource to this particular process, but did not get better result. Actually get worse result. Okay, so that's the characteristic of first in first out. Okay, the embedded is a person which find out this anomaly. Okay, so this anomaly was named by this scholar. Okay. Okay. Now let's look at this particular reference tree. Okay, and for first in first out, we and compare with optimal scheduling. Okay, so here for first in first out with 3 friends, then this physical friend we will generate this 15 page 4s. Okay, and with the optima means, okay, when we try to when there's a page 4, okay, in here in the first page in 7, 0, 1, they all generate page 4, and then 2 will generate page 4, but instead of replace in the here the next reference for 7G1, 0 and 1, the far is 1 is 7, so we replace the position of 7 by 2. So now the physical frame is 201. So that's why the next reference 0 will not generate. Okay, and then 3 would require a page 4 because it is not in the memory. Okay, but we will look at 201. We find out 1 is the file is 1, so the position of page 1 was replaced by page 3. Now the free frame is 203, contain 2, 3, 20 and 3. Okay, then 0 without, then 4 also generate page 4. Now look at it, check the 203. We want 203. 0 page 0 is the file is 1, so the page 4 replace the page 0, the position of page 0. We get physical frame contain pages of 2, 4, and 3, and then 2 and 3 will not generate page 4. Now get 0. 0 generate page 4 because 0 is not in the physical frame. Okay, so starting from this position, we check 2, 4, 3. 2, 4, 3, we find out the longest one is 4 because we never try to access page 4. Okay, so the 0 will replace the page 4. Okay, the physical frame become 203. And so follow the 3 and 2 will not generate, but 1 will generate page 4. And then we check 203. 203 we find out 3 is not appear, not occurred. So 1 replace 3. Physical frame become 201. Then 201 7. 7 will try to generate a page 4 and check 201. 2 not in the distance. So 7 will replace page 2. Okay, so but optima for this same reference stream, 5-4 generate 15 page 4, but optima only generate 9 page 4. So it's far, the number of page 4 is much smaller. Okay, so and it is an upper bound at the base. Okay.